Hi, this is lesson 6, Newton's second law. I'm sure all of you know this by now, but Newton's second law, the greatest law in all of physics, F equals ma. F equals ma tells you a lot of different things. Firstly, it really, at a very fundamental level, defines what a force is. A force is something which accelerates a mass. So whenever a mass experiences an acceleration, which remember is speeding up, slowing down, or changing direction, things that you can feel, you know there must be a force there. But it tells us a lot of other things too. The first thing is it tells us that these three things are all proportional. For a given force, if we double the mass, we're going to have to halve the acceleration. For a given acceleration, if we double the mass, we'll have to double the force. If I plot a graph of force against acceleration, just take a moment, what shape will it be, and what will the gradient be? Just pause the video, have a little think. Pretty simple one here. It's going to be a line like this, straight line, and the gradient is just going to equal the mass. Not sure about that. We've got F equals ma, so we can rearrange it. So m equals F over a. And we know whenever we're doing a gradient, it's the change in y divided by the change in x. Pretty simple stuff there. So it tells us that there's this relationship between the three things as well. But there's something else really interesting going on here as well. I'd like you to look at these four equations and just have a moment to think, what makes these two at the bottom different from these two at the top? Can you spot it? Just pause the video, have a moment. The answer is that these two both have a constant, g, and 1 over 4 pi epsilon naught. The question I want to ask you now is, are constants real? What does a constant do? Pause the video, just have a little think. What is the point of a constant? The answer is quite simple on one level. It's to make the units work. Yeah, so look at this one. If we've got a force in newtons, two masses in kilograms, and a distance in meters, the numbers will only work if we times it by this completely arbitrary number g. Exactly the same thing's going on over here. We've got two charges, both in coulombs, distance in meters, force in newtons. We've got to put all this rubbish in here, the 4, the pi, and the epsilon naught, just to make the numbers work. Whereas interestingly, we don't have to do it in these two. Now here's a tricky question for you. Why do these two not have units? Sorry, these two not have a constant, and these two have a constant. Pause the video and have a think. The answer, by the way, is not just because the numbers already work. There's something more subtle going on, so just have a think, see if you can get it. The answer is because that's how we've defined them. We decided that 1 Newton was going to be equal to 1 kilogram meter per second squared. We just defined the units that way. We could have done it completely differently. If we were a race of aliens and we spent all our time in space with things swinging around each other, we might think it would be a more useful set of physics to define forces in terms of kilograms squared divided by meters squared, and then we could just put this g over here instead. We could do it any way round we wanted. It's really important to remember that things like newtons, joules, kilograms, and meters are arbitrary. There's nothing real about any of them. We've just decided that these things should come in lumps that big. And these things come from all sorts of places. Where do you think the idea of a meter comes from? If you go back and look at the history of it, it starts out with people measuring things in hands, and then feet and inches, and then finally we get something a bit more standardised with the metric system, which if you look is relatively recent. But it's still arbitrary. We've talked before about le kilogramme, which is literally just a lump of metal in Paris. That's all a kilogram is. It's not real. So here's a question for you. Imagine you were an alien and you were designing physics from scratch. Would you still get the same shape of graph? Take a moment, pause the video. The answer is yes. Yes, you would. This law, this relationship is actually immutable. The graph might pitch up and down, be at a different angle depending on how you defined your units, but the shape is going to be exactly the same. That's magic. There's something wonderful, I find, that physics is the same wherever you are in the universe. You're going to get the same sets of equations, and while the constants might be different, because on planet Blark, you think the fundamental unit of length should be this long, not this long, but everything else is going to be exactly the same. I think that's really neat. I'll see you tomorrow.